Okay, today we're looking at momentum and impulse. This is part of the further maths mechanics from A-level. So momentum is a measure that takes into account both the mass of an object and the velocity of an object. So the momentum is defined as the velocity multiplied by the mass. Now, one thing to note about this is velocity is a vector quantity, mass is a scalar, which means technically momentum is a vector quantity. Okay, this is just a scalar product of a vector. Okay, so therefore this is a vector, therefore momentum must also be a vector. Now on this course, most of the momentum that we deal with is all in one dimension, so you might just have a positive or negative value for momentum. But just bear in mind that you can have two-dimensional, three-dimensional momentum cases, but just not in this course. Okay, so momentum is defined, that's how it's defined, as velocity times mass, and the impulse, this has two definitions. So the impulse is something that occurs when a change in momentum happens. And definition number one is it's the change in momentum. Okay, so that is essentially momentum after the event, subtract momentum before the event, whatever the event is. It's usually a collision on this course, but it might not necessarily be a collision. But impulse has another definition as well, which you need to be aware of, and that is force times time. And we use this definition and this definition of momentum in conjunction with one another quite often to find perhaps unknown forces or unknown times, given some details about the velocity, momentum, etc. Now, because momentum is a vector and this is a change in momentum, then impulse is also a vector, and we can look at this as being a vector times a scalar. So therefore, impulse is a vector. Okay, so these are vector quantities. Okay, so it does matter when you're asked, for example, what is the impulse that acted on such and such an object, you must state which direction that is acting in. Okay, so let's have a look at some basic questions on this topic then. Okay, so we've got a train. It's got a mass of 1,000 tons and is travelling at 35 meters per second. Calculate the momentum of the train. So momentum by the formula is mass times velocity. So momentum is going to be mass multiplied by velocity. Now, usually we deal with SI units, so we need to convert the 1,000 tons into kilograms. So that is 1 million tons, 1 million kilograms. And we're going to times that by the velocity, which is already in SI units. That is 35. So the momentum is 35 million, and the units of momentum are Newton seconds, or sometimes we might have them as meters per second times kilograms. Okay, and we can see this definition from the units from here. We've got meters per second and we're timesing it by a kilogram. Okay, so either one of these two units is used. This one is more typically used for momentum and impulse. So this is the momentum of the train. Okay, it's a high momentum because it's got a high mass. The velocity is fairly large. It's probably about 70 miles an hour, maybe a bit more. But it's the mass of the train that gives it its momentum in this case. Okay. Right, example number 2. A ball with a mass of 50 grams is hit with a force of 20 newtons for 3/20ths of a second. Given that the ball was stationary before the impact, calculate the speed of the ball after the impact. Okay, so this time we're going to use that the impulse is defined as being equal to the change in momentum. Okay, now impulse is force times time. So that's going to be 20 times 3/20. And the momentum, well, that's going to be the momentum afterwards, which is 0.05, which is the mass, times the velocity, plus 0.05, subtract, times 0. So this is the initial momentum, which is 0 because it was stationary before the impact. And this is the final momentum, which is going to be the mass in kilograms multiplied by my unknown velocity. Okay, so this gives us an equation with just v in it. The 20 and the 20th cancel, so that just is 3 on the left-hand side. So I've times both sides by 20. I'll get v is equal to 60. And that is a velocity, so that is meters per second. Okay, there we go. So that is the velocity of the ball after the impact. Okay, immediately after the impact as well. All right. All right, and one final example question. A ball of mass 100 grams is dropped from 2 meters above flat horizontal ground. Calculate the speed of the ball when it first hits the floor, and you may assume that air resistance is negligible. Okay, so my answer to part A, this is going to be a SUVAT problem. So it's got, it's dropped. Let's assume that it's got an initial velocity of 0. It's 2 meters above flat horizontal ground. So let's do our SUVAT table. It's falling 2 meters. I'm taking down to be positive. It's got an initial velocity of 0. That's what I'm trying to find. And it's got an acceleration of minus 9.8. And I don't care about how long it takes. Okay, there's no interest in that for part A. So I want a SUVAT equation which contains everything here, not a t. So that SUVAT equation is going to be v squared equals u squared plus 2as. So therefore v, so it's positive, 9.8, apologies. I'm taking down to be positive, so that's positive 9.8. V is going to be the square root of 2 times 9.8 times 2. Okay, let's put that into my calculator. So 2 times 9.8 times 2 is 39.2. I need to square root that, which comes out to be about 6.26 to 3 sig fig. And that's a velocity, so that's in meters per second. To 3 significant figures. Brilliant. Right, so that's my answer to part A. Part B. Given the speed of the ball after impact is 4 meters per second, calculate the impulse on the ball during the collision. Okay, so what we've got, might be useful to draw a little diagram here, is we've got a ball coming down, it's hitting the ground, it's got a mass of 100 grams, and then it hits the floor, and then it's going to bounce back up with a new speed. And I want to calculate the impulse on the ball during this collision, during this bounce. Okay, so we just calculated that the speed it hits the floor at is 6.26, and then we're told that the speed it leaves the ground at is 4. Now the impulse equals change in momentum. And now it matters now, just be careful which direction is positive. Don't forget, at the beginning of the video, I did explain that momentum is a vector. So these are in opposite directions. So that matters. So momentum afterwards is going to be the velocity times the mass. Subtract the momentum before, which is the velocity, which is minus 6.26 times the mass. Okay, I'm subtracting a negative because, well, in this calculation, I'm taking up to be positive, which means I'm going to end up adding this number to it. Okay, so just be careful with that. Okay, they're both acting in opposite directions, these speeds, so therefore the change in momentum is going to compound from both of those. So I could factor the 0.1 out. So I've got 4 plus 6.26 times 0.1. And that gives me 1.026 is the impulse. That's in Newton seconds. And again, just going to re-emphasize, this is going to be upwards. Okay. The impulse on the ball is acting upwards because the change in momentum is acting in this direction. Okay, it was coming down and it's now moving up. There's been a change in momentum that way, so therefore that is the direction of the impulse on the ball. Okay. And then finally, part C. The ball was in contact with the floor for half a second. Calculate the average force of the ball from the ground. So this is where our other definition of impulse comes in. So impulse equals force times time. I've got an unknown force, I know my time, and I know my impulse. So I get 1.026. That's going to equal my unknown force times my time, which I know is 0.5. So the average force is just going to be that answer times 2, which is 2.052. And that is going to be newtons. It is the average force because, well, we don't actually know what the force is over time. There's not enough information here. What's going to happen in reality is the force is going to get bigger. It's going to peak at about 1/4 of a second, and then it's going to start to decrease again. Later on in mechanics, but not on this course, you deal with impulse as being the integral of force with respect to time between two t values, t1 and t2, so it's the area under the curve. What essentially we're doing here is we're calculating what average force that would be across that time period to give us that impulse. Okay, right, that's it for this video. Thank you very much for watching, and check out my next video, which is on the conservation of momentum.